Okay, so let's have a look. So we've got our M kilogram mass here, capital M, mg, so acting down, T acting up. So we'll call that system 1, and we'll call direction of motion acting down on the left side. System 2, tension again acting up the string, and lowercase mg acting down. So there's all of my different weight forces. All right. Find an expression for the acceleration of the system in terms of m. So capital M is bigger than small m. So again, acting down is positive, so mg minus t equals capital MA. On the second system, t minus mg equals lowercase ma. And so we've got tension, which is common. All right, and obviously acceleration. So if we add those two systems together, we'll get capital Mg minus lowercase mg equals m plus ma. Take out a and g as common factors, and then we get an expression for a. So if m is equal to 2m, well, we can just substitute that in. Capital M equal to lowercase m. We'll get our m, so that we get an acceleration. And then obviously if we've got an acceleration, we can solve for the tension in terms of lowercase m. All right, so pick the equation that has lowercase m in it. All right, so hopefully that falls out all right for you. All right, we've got our mass on a inclined plane, so we've got to draw all the forces. So again, if we look at the capital M, we have mg, okay, so I've got our mg acting down, okay, our resultant force acting perpendicular to the plane. We have tension acting up the string. We've got the same tension acting up the string, and we've got a lowercase mg acting down. All right. So we've got two systems. All right. And what relates the two systems are the tensions across the string. All right, because they're the same tension. All right. So capital M is bigger than lowercase m, show that sine theta equals. So don't forget that when we resolve our forces, let's make horizontal to the plane. For system 1, we're talking horizontal to the plane. So I've got lowercase, or so capital M, mg sine theta acting down the plane. I've got tension acting up the plane, and that's equal to ma. All right. If I work system 2, I've got tension acting up minus mg acting down, it also equals ma. So I've got a rule for tension. Tension is equal to ma plus mg. So horizontal by side pass over small forward, other than the string mass and hangs work, given that it show that side theta. So we'll still work on that. So we've got trying to work out why acceleration was 0, but our particle was in rest, isn't it? The particle is out in rest, so acceleration is equal to 0. So if we sub into 1, so we're going to have t is equal to mg, aren't we? So if we put that over here into equation 1, I get mg sine theta minus lowercase mg equal to 0. Solve for sine theta, and we'll get sine theta equals lowercase m on m. All right. All right, Louis in a lift. When the lift accelerates upwards, the reaction force of the lift on the floor on Louis is 650. When the lift accelerates downwards, same acceleration. With same acceleration, the reaction force of the lift floor on Louis is 625. Find the mass of Louis and the acceleration. All right, so system 1. So let's just go with system 1. System 1, acceleration is acting up, so we'll make positive as up. So I get 650 newtons minus mg is equal to ma. Okay. System 2, again, keep positive up. I've got 624 newtons, again, minus mg is still equal to ma, but acceleration is downwards this time, so we're going to have minus ma. All right. If I add them together, what does that give me? It gives me The MA's cancel. I get 2 mg is equal to 1274. So that I get a mass of the object there at 65 kilograms. All right, so then if the mass is 65, I can substitute that into equation 1, and then I can solve for A, and A is equal to 1/5 meters per second squared. All right. All right, what have we got? A bowling machine is programmed to project the ball from a height of 1.5 meters above the ground at an angle of 30 degrees to the horizontal as shown. Initial speed is 8, travel projection, Cartesian plane. J is vertical, I is horizontal. Okay, show that the ball has an initial velocity when produced. So what's the velocity of the ball? Yeah, so the velocity is 8 meters per second. So that's 8 meters per second at an angle of 30 degrees. So the adjacent side, cos 30 times 8, cos of 30 root 3 on 2. So 4 root 3i. Vertical, opposite side, sine 30 times A is a half. So there's my 4 root 3i plus 4j. All right. Acceleration of the ball is given by blah, blah. Show that the position vector of the ball is given by. Okay, so there's the acceleration. So r dot, okay, is going to be the integral of the acceleration, isn't it? So t squared on 100, t squared on 2 minus gt. So just integrate each expression plus some constant. We worked out previously on the previous page what my initial velocity was. So at t equal to 0, velocity is 4 root 3i plus 4j. So that means at t equal to 0, c will equal those, won't they? So in fact, that expression there is equal to c. So if we incorporate that into my velocity vector, dot of t, I get 4 root 3 minus t squared on 100. So I get this expression here. Now I work out my position. So I'm going to integrate again. So just be careful, add to the power, divide by the new power, all those wonderful things. And at t equal to 0, the position of the particle is 1.5 meters off the ground. So 1.5j. So that makes t equal to 1.5j. So I can incorporate that into my j component of my position. So over here in red is the position, which is what given to me up there. All right. How far does the ball travel horizontally before it hits the ground? Okay, so when does it hit the ground is when the j component is 0. So if we solve the j component equal to 0, I get 1.0973 seconds. And if I put t equal to 1.09 into my I component, I get 7.597 meters. All right, so it travels 7.6 meters. All right, for 2 marks, clearly finding the t and putting it back in are the relevant marks. So we're solving on our CAS. What is the distance in meters that the ball travels from when it is projected until it hits the ground? Give your answer correct to 1 decimal place. So how far is the ball traveled? Not the horizontal distance, the ball. So it's the length of the curve, isn't it? So the length of the curve between A and B, the integral of the square root of, what are we going to say? dx dt all squared plus dy dt all squared. So again, just set up the equation right, square them straight into a calculator, and I get my 8.4 meters. All right. Find the speed of the ball in meters per second when it hits the ground. So at t equal to 1.097, I want to substitute 1.097 into a rule that will give me the speed, so the magnitude of the velocity. So again, just it's a calculator exercise. We're going to substitute in the t values that have been given, and we end up with 9.6 meters per second if we've worked that out on our calculator correctly. All right, what have we got here? A particle of masses 4 and 7 are both shown on smooth planes, so there's no friction. The planes are inclined at the horizontal angle of theta and 2 theta respectively, where theta is somewhere between 0 and 45. which makes sense because 2 theta would be 90. A light string, it passes over a smooth pulley that connects the two particles. Tension in the string is T newtons. A 7 kilogram mass accelerates down the plane. So we're going to travel this way, okay? All right, so let's just set up the two systems. So again, we have a resultant force. I have a force that's perpendicular. I have a tension force. I've got my perpendicular and parallel components. So of course, in reality, that's 7 kilos. That's that, isn't it? 7 G's acting that way, 4 G's acting that way, but resolving. We're going to resolve parallel and perpendicular to the plane. So if we stick to the 2 theta block, okay, up the plane, I've got tension acting up the plane. So don't forget that's positive, minus 4G sine 2 theta acting down the plane is equal to 4A, or alpha, A, whatever our acceleration is given by. So if we rearrange that, so there's my equation, and we could just write tension is equal to, so there's my equation of motion, but I'm going to rearrange because I'm going to substitute that in later. Hence show that the acceleration of the 7 kilogram mass down the plane is given by, so let's look at the 7 kilo mass. If we look at the 7G sine, all right, so there's the parallel to the plane, isn't it? So I've got 7G acting down minus the tension acting up equals MA. So that's again, sum of the forces equals MA. And then obviously I've got an expression there for T, so I can grab that T expression here from the first part and substitute it in because it's the same tension. So minus 4 minus 4G. So if I simplify things a little bit, for sine 2 theta, I want to get them as 2 sine theta cos theta. So again, I can take a sine theta out the front as a common factor and get my 7 minus 8 cos theta. So you can see this, I end up with that expression here if I just pay attention to a little bit of detail and just be careful. Find the angle theta when the system's in equilibrium. Okay, so acceleration is 0. So I want to solve that expression there equal to 0. So what does that mean? It means either G sine theta on 11 is equal to 0 or 7 minus 8 cos theta equal to 0. So the first one gives me angles, values of 0 and pi. The second one gives me cos inverse of 7/8, which is 29 degrees. Now, theta itself is between 0 and 90 degrees, isn't it? Well, in fact, I'd imagine 0 is not inclusive. No, it's not. Because if it was 0 degrees, we're just on a flat horizontal surface. So, not valid. So my angle is 29 degrees. All right, suppose theta is fixed at 30 degrees and the mass of M is added to the 4 kilo mass. The 7 kilo mass now accelerates up the plane with an acceleration of, find the value of M. So I've brought this diagram in here again now. So this time we're moving up the plane. All right, so everything else is the same. T is going to be the common link. So system 1, I've got mg sine theta, and M is equal to, don't forget that's plus M. See the plus M there? So mg is 4 plus mg sine 60 because it's 2 theta, minus T is going to be equal to the weight force down the other side. No, is equal to MA. And if we have a look at the second particle, system 2, I've got upping up the plane, so a positive tension minus mg sine theta, which is 7g, equals 7a. So this one here gives me very quickly, sine 30 is a half. I get tension is 7a plus 7 on 2g. So that's what I'm going to be able to substitute into the first equation. All right, so group some terms together. So sine of 60 is root 3 on 2, so there's my root 3 on 2g times 4 plus m, minus t, which is minus 7a minus 7 on 2g, equals 4a plus ma. So if we needed to get an actual value, we could just rearrange it on our CAS, okay? Which is possibly what we would do here. If you just want to be a bit careful, so 4 times 2 is 4 times a half is 2, so I get 2 root 3g. I've got m. I'm going to take this root 3 on 2gm over to the right-hand side. I've got this 4a can come across, so it gives me a minus 11a minus 7 on 2g. I could group the g's together, take g out as a common factor. So I get 2 root 3 minus 7 on 2. Okay, and then we've got minus 11a. That's the acceleration term. What have I done in here? It looks like we've taken an m out the front, g out the front, and substitute my acceleration in. So you can work through it if you want, but in reality, boys, it's not going to be work through it if you want to practice the algebra of it. But you would solve it on your CAS and just get an expression for m. All right. Yeah. Talk to me if you want to have a discussion about it.